18.7, Bernoulli's equation. 27, for laminar flow of a non-viscous liquid through a tube in which the cross-sectional area at point 1 is different from the cross-sectional area at point 2, how does the mass of liquid flowing past point 1 at a given instant differ from the mass of liquid flowing past point 2 at that instant? They are not different, they are the same. The masses are the same. Remember, for laminar flow, we don't have, well, for turbulent flow, if you recall, we've got flow that's kind of chaotic, right? And so you could have this kind of a bunching up effect. And so, but for laminar flow, there's no bunching up. So even if you have this constricted flow like that, if you recall in the earlier videos in the earlier section, the amount of mass flowing through a point during a time interval delta t, that mass will be the same as the mass flowing over past this point at delta t. Okay? So it's the same. Okay. 28. An aqueduct of constant diameter. Alright, so it's basically some kind of pipe, huge pipe that's transporting water. It has a constant diameter, is at some points along its length very close to the ground, and at other points far above the ground. If the flow of water in the duct is laminar, how does the water pressure at some point, at some location 1 along the duct length, compare with the water pressure at some other location along the length? Okay, so remember, so we're dealing with laminar flow. We can use Bernoulli's equation. What is Bernoulli's equation again? It's pressure at point 1 plus density, gravity, height at point 1 plus half rho V1 squared is equal to pressure 2 plus rho Gy2 plus half rho V2 squared. Okay, but we also can use the continuity equation, which is A1 V1 equal to A2 V2. So this is very helpful. As long as we have laminar flow, as long as we've got laminar flow, this is valid. Okay, so as you can see in this equation here, we've got these velocities. So say now you've got this pipe of constant diameter and it rises to another height. Okay, constant diameter, there's point 1 and there's point 2. Then what are the velocities between these 2 points? Well, as long as we've got laminar flow, we can use this continuity equation to look at the velocities. And as long as if the areas are the same, then V1 equals V2. Does that make sense? So A1 V1 is A2 V2, and if A1 equals A2, then we can divide by those values, and so V1 equals V2. So the velocity, we can chuck that away because they're the same. And now we're left with pressure plus rho Gy equals pressure plus rho Gy. And if the height at point 2 is greater than at point 1, then if this term is higher than that term, then that term must be lower than that term. Okay? If that is higher than that term, let me make sure you see where I am. If that term is higher than that term, then that term must be lower than that term, because they're equal. And so this is saying that constant diameter, laminar flow, at the higher position, the pressure is lower than there. At the higher position, the pressure is going to be lower than at that point. Okay. Finally, 29, a horizontal aqueduct Horizontal is constructed of pipes that have different diameters. Okay, so something like this, or why don't we do it this way rather? Something like this, different diameters. Okay, different diameters. If the water flow in the duct is laminar, how does the water pressure in a small diameter portion compare with the water pressure in the large diameter portion? So remember that the pressure over here is going to be greater because we have the speed is going to be lower, right? So the pressure over here is higher and the pressure over here is lower. Okay, so let me just check exactly. It says the pressure is lower in the smaller diameter portion because the flow speed is higher here, and the flow speed and it's going to be higher here because the flow speed is lower. Okay, so good luck with everything.